Excellent. How many 150s were there? Alan, was that you? Anybody else with 150? Just a 150. Beautiful. 155. 60. There was 160, I thought, right? A couple 160s. 65s. 2. Good. 170s. Ah, interesting. 1, 2, 3, 4, 5, 6. 75. That's where I actually am closest to. 2, 4. 80. 4. 85. 1, 2, 3, 4, 5. Oh, good. And 90. Well, at least 190, right? There we go. Beautiful. Let's take a look at it. Let's take a look at it. It's got a little double hump. It might not be far enough away from a bell curve again. It might again be bell-shaped. This one usually tends to not be, historically. That doesn't mean squat, as we learned from looking at investments over the years. But let's see. Let's see. Past performance governs future results. Curious. I should save this for next class. Nah, look at their own data. We're in 5-pound increments. Nice. Nice. I'm going to finagle because I'm me. This is good. That's fun. There's us. There we are. Anybody weird? Outliers, guesses? Any outliers? We do have a low value, correct? We have a low value. And we have a high value. Is the low unusually low? Is the high unusually high?
Compared to what?
Well, that's the whole thing. Compared to what, right? Do we look at it just as distance from the majority? We got distance here. Do we compare it as different value? We only have this 190, but we've got this sizable chunk of 5 185s just below it. Is that meaningfully different? Compared to what? Well, let's what do you guys say? Bell shape?
No.
We have a vote for no. Jolene says no. Quickly, no. Carly, go.
I think that 150 is an outlier, but 190 is not.
Okay, so go ahead. And how come?
Because the interquartile range is 170 to 182.5, and that plus 50% does not include 150, but I think it includes 190.
Damn. Some good talking back there. Check this out, check this out. As soon as I asked, is the data bell-shaped, Jolene says, no, it doesn't look bell-shaped enough. Who says it is? Who says, yes, it's bell-shaped enough? You don't have to agree or disagree with Jolene. I'm saying this is, nobody said, okay, it's not shaped enough. Beautiful. Thank you. His history has proven to be a worthy predictor of what this is going to look like. So if it's not bell-shaped, what do? Well, we have two other choices, only one of which I want to get into right now. Carly's mentioning it. If you don't have bell-shaped data, and believe it or not, even if you do have bell-shaped data, this will work too. This will work in general for all shapes of data. That one only works for bell-shaped. But if you do, or if you don't have bell-shaped data, you do have a fallback. And this also answers Pat's question, compared to what? And the answer is compared to the entire data set. Good. See, the problem with the first way is, oof, God, I'm really close to that camera. The problem with the first way is it doesn't compare the data points to all the other data points' values, just their average distances from an average. Hence the definition of standard deviation. This one, the way Carly's defined it, actually talks not about those absolute positions. Not about those absolute positions, but instead the relative position of smallest to largest. So it's a slight difference, a little lack of detail, a tiny bit of lost detail, yes? Tiny bit of lost detail, because the absolute values are now lost. But if you've lost the ability to analyze because of the lack of bell curve, this gives us something. Beautiful. Now, outlier ID number 2. Outlier ID number 2. All right. This one depends not on an average and a standard deviation, but instead on percentile rank. Okay? I'm going to put that just in parentheses up here. This depends on percentile rank. Now, just like the 2 standard deviation idea, exactly like that, the goal of the outlier ID is to set up fences. The idea is set up fences. You trap fences. And between the fences are the normal data. And when I say normal, I mean typical. I shouldn't say normal. That's a terrible use of the word. So you set up a low and a high. Between the fence posts are the typical non-outlier data points. Outside of the fence post are the ones that are too big or too small. Fair enough so far? Good enough so far. Okay, good. So the idea is we can't set up the fence posts with the mean and the standard deviation because the mean and the standard deviation might not be trustworthy in skewed data. So we vote that off the island and we say, okay, let's set it up a different way. So here's the sequence of steps to set up the fence posts. Step number 1. Find your IQR. Now you might not remember what that is from last time, and it's okay. Remember what it stands for? Awesome, interquartile range. I didn't make you memorize it. You're not going to memorize it because the technology does it automatically for us after this first foray into the mathematics. It's the interquartile range. Spelled that wrong. Quartile range. So Nick, when you said earlier, I think it has to do with range. Hell yeah, it does. So you do your Q3 minus your Q1. You find the 75th percentile distance from the 25th percentile, which tells you where the middle 50% of your data is. So you're going to have to run one of our stats to get these numbers. Okay, so let's do that. All right, you guys guessed 174.2. Not bad on average. Even with the non-bell-shaped idea, you still got pretty close to me. Here's what I'm interested in. My median's, I'm almost always around 175 within 3 or 4 pounds of that. So here's your interquartile range. 50% of your guesses were between 170 and 182.5 pounds. Why is it 182.5? Nobody guessed 182.5, did they? How could you have 182.5? That's kind of weird, isn't it? Yes! Because the 75th percentile was between 180 and 185, and you take the average of those two, just like back in the day with the medians. It's a median, if you think of it that way. So computationally, it just is between the 180 and the 185. Exactly, Doc.
Why? Because there's 9 data points there, and
yeah, well, there's 25 total.
Right.
So you find the 13th to set the median. Then you've got 12 and 12, which means you have to go between the bottom 6 and the top 6. So if you go to the top half, the highest element in the 3rd bin was 180. The lowest element in the 4th bin was 185. So the median of those is 182.5.
That makes sense.
That makes sense. Good. Excellent. So anyway, our IQR is the distance with 12.5 pounds. 12.5 pounds. 12.5 pounds. Love it. Now that kind of sounds like a what? It does, doesn't it? It kind of sounds like a standard deviation. That's the offness of the median. You know, you guys were 12.5 pounds around the median. The problem is, if you're trying to compare this back to the idea of setting up fences from a standard deviation, what does 2 standard deviations capture, percentage-wise? Two standard deviation. 95%. Yes, one standard deviation. Yes, 2/3. 95%. So the kicker is, if we go back to 1 standard deviation, 2/3 of the data is 68, 67%, somewhere in there. This is still too small. It's 50%, not enough. Now here's where the discussion comes in as to, we need to multiply this by something. We need to multiply this by something to make it bigger to stack. And I've seen this change 3-4 times in the past 20 years of studying mathematics. Right now, the current multiplier is at 1.5. That's the 50% more that Colin was talking about before. Good. So Pat, here's step 2. Just like we multiply 2 times the standard deviation over there to bump us out, we multiply this by 1.5. That's right now the accepted multiplier. I've seen it as high as 3. I've seen it above 3. I think people are realizing if you make it too big, you start calling everything normal. Right. And then nothing's unusual, and then you start missing things that are unusual, like Jared. So, take 1.5 times the IQR and figure out what that is. So this is the 50% over the 12.5. So that's 12, that's 1.5 times 12.5. So remember what I was doing with my fingers in the boxes last week with the quiz? I was trying to guess which groups had outliers, and I took the box and then stretched it 50%. This is what I was doing, trying to do geometrically. Remember? Marley, go.
So, can you please explain the 1.5?
I wish I could better. It's the now, remember how I said 95% trapped is the new industry standard? This is the industry standard.
So
1.5 is the multiplier.
1.5 is a constant.
It's a constant, yes, it's a constant. You take the 12.5, you take the IQR, and increase that range by 50%.
So the 1.5 is representing
150% of the IQR.
Can I answer it?
You please, yes.
When we did the box and whisker plots,
Yes.
they showed up as boxes, and then on the outside were the whiskers.
Yes.
So the box represents the inner quartile range.
Yes.
But in order to capture more data, we increase the size of the box by 50%.
Exactly.
We take half of the box and we add it to the outside of the box, and that's where 1.5 comes from.
Mhm.
Is that?
The problem is,
Makes
it's
sense.
not, there's no mathematical reason for it. It's just been settled. I think, but the question is, why 1.5? Why not 2? Why not 2.5? Why not 1.75? And I don't have a good answer for that, other than that's what the industry standard is right now, is you have to increase it by something to capture more data. 1.5, we're settled on 1.5. Nick, go ahead.
Couldn't it be because the maximum standard deviation you can go out is 3, so you just take half of that?
Don't apples oranges. Standard deviations over here if we have bell-shaped data. We're not even talking about standard deviation. We're trying to set up a system that's like that we can stack, but we're not there here, if that makes sense.
Oh yeah, I understand.
I love what you're saying, Nick. What you're saying makes sense, but it's a parallel to that. It's not equivalent, though. Is that fair? Thank you, sir. Thank you. Please, Veronica,
Well, we
go.
have to determine at some point what the cutoff is.
Exactly.
So it just has to, a group of people determine. But
And that pisses me off. YouTube world, I apologize for this. Statistics is full of numbers that have been handed down to us. 95% 2 standard deviations is a standard. N equals 30. You'll see that one later in the course. N equals 30 for sample sizes. 1.5 for this. They've been handed down. And one of the criticisms of statistics is, where do these arbitrary constants come from? I don't know. I mean, I can tell you where 95% came from. It came from Ronald Fisher, who handed it down to us 100 plus years ago. And it's kind of like, why do we also measure in feet and inches? Because we always have. And it's too much of a pain in the ass to change now. The rest of the world uses metric. Even the friggin' English don't use the English system, they use the metric system. But it's just too hard to change now, unfortunately. So that's why part of me is like, it rips me up to teach this to you, but at the same time, if I don't, then you're ill-prepared to consume the journals that you're gonna have to consume. Does that make sense?
Yep.
So yeah, there is a line in the sand, and this happens to be it right now. Fair?
That's
Right now.
the
I mean, and like I said, I've seen it change.
Right.
I've seen it change. When it changes, I change the curriculum. But right now, it's staying consistent at the 1.5. So that ends up being what? 6 and 18.75? Did I do that right?
Yeah.
That is going to become our plus and our minus. That's going to become our plus and our minus.
Okay.
Now the question is, what does it add and subtract from? Do you remember this from last class? Of course you could say no, because that was 25 inches of snow ago. No, you don't remember. Remember what I did with the box? I had the box, and then I stacked it somewhere.
On top.
On top of who and on top of whom?
The median.
Not the median. That would be the first guess and the most logical guess. It was, you remember, Carly?
It's the first quartile.
It was the quartiles I stacked it on. When I had the box plot in front of me, I took the IQR, increased it by 50%, and then stacked it on the quartiles. Why not the median? I don't have a good answer for that. It's not how it's done. It's not why we drive on the right side of the road. Because we do. So you stack that on the quartiles. So step 3 is set your fences up. And you need 2 fences. One above the 3rd quartile and one below the 1st quartile. So you've got to take Q3 plus that number you just calculated. You take Q3 plus the number you just calculated. That sets your high fence. So your high fence is going to be, the Q3 was 182.5 plus this guy, which ends up being, if I do my math right, 201.25. Did I do that right? Did I do that right? I think I did. Carry the 1, carry the 1. Check my math if you would. Yeah, thank you, David. I don't trust my arithmetic, you shouldn't either. This is why we have computers. They'll take it taken care of for us, but I also like you to know what the hell's going on with the computers. We'll come back to that number. Because the problem right now is that I feel the frustration in the class. We're getting lost in the math. We're getting lost in the computation. Not much math, but we're losing the forest for the trees, so to speak. Like, great, we know what 201.25 is. Why did we ever want that in the first place? Come back. Let's get the low fence. That's the high fence. Low fence has to come off of Q1. Ask me questions as you think of them, friends. Ask me questions as you think of them.
What do you mean by high fence?
Remember with the two standard deviations, Marty, we set the two, those are the critical values? We're setting the critical values right now in this method. So we have the rightmost one, now we're on the leftmost one. Is that fair?
Yes.
And I apologize for the tediousness of this calculation. It's a bit prescribed. Kind of annoying. Fair enough?
Yep.
Excellent. Good. Now we do Q1, which was the 170, minus the 18.75 pounds. So let me make sure I do this right.
151.
Thank you. 0.25.
Yep.
There we go. There's our low fence. Here's our high fence, which means we now have boundaries on our graph for what would be considered typical weight guesses.
Right.
Now, get a deep breath. Thank God, there's a lot of math. It wasn't that much math, actually. It's annoying math. And the problem with me, many problems, but one of the problems with me is I always want to know why things are, and I hate having to say it's like this because it's like this. I hate that. It's like when your parents tell you, why can't I go out? Because I said so. Give me a reason. Because you're going to die. That's a good reason. I can't give you a good reason for the 1.5. I've seen it fluctuate historically. Linda, go.
You said high.
Fence. We'll come back to what this means in a second. And low fence. Ariel,
So
go.
we're not calling it a standard deviation.
It's not really. It's serving the same purpose as that. I don't know what to call it. I made up this word fence.
Okay.
And I tend to use the word fence or critical values interchangeably depending on the method. Because what I look for is I try to figure out ways things are the same. The idea is you take your data set and you create two values beyond which the unusual lies. That's what we've just done. We've set two values in our data set, which I now want to look at. There's our data set, yes?
Yeah.
Now let's go back to this.